All right, we're back. It is game 2005. That's game physics. It's not to be confused with a physics engine building kind of course, right? And we are in the fall 2017 semester at George Brown. We are week 2, part 1 of our broadcast, and we are talking about limits and derivatives today, moving away from trigonometry. So the trigonometry section is done. It was an intro to get you going with algorithms, just basic algorithms for trig, functions, algebra, basic algebra that we covered last week. And this week we're talking about limits and derivatives. I will post this PowerPoint, like I said, at probably the end of the day. All right, so what are we talking about when we speak about limits and derivatives? So we want realistic motion. You know, as an example, we want to often find, see if I can make this a little bigger. We often want to find velocity, which is a rate of change of position. So we have a position function, some position function. And let's say, for example, we want to move our aliens around in a certain pattern. And we want to find how fast they're going for whatever reason. Maybe we want to calculate something like where they're going to be in a particular frame. And so we need to know how to calculate their velocity from their position function, right? Further than that, what if we want to find, for whatever reason, the acceleration function, so we can calculate things like momentum and other things, other kinds of patterns of movement and force, right? Well, we need to somehow derive, this is where the derivatives come from, derive one equation, one function from another, right? So given that we're going to be given the position function, let's assume we want to find acceleration, and that's the rate, the instantaneous rate of change of velocity. Here are my words, instantaneous rate of change, which is kind of like the average rate of change for that particular point in space, right? To find velocity from position and so on. Okay, so that's really why we use limits and derivatives. We use them so we can find one function from the other, and that's the most practical use of them. We're not talking about position or acceleration today, or even velocity or anything like that, really. We're just talking about ways of figuring out, just like we did last week when we talked about the triangles and how to use triangles in nature, how to figure out how to solve triangles. We talked about that last week. So this week we're going to be talking about, let's take that a little further now, using some of the things we talked about last week and combine them with new things, if you've never seen calculus before, to help us determine some other things. Now, this is going to be the boring part. So let's suppose if we don't know acceleration or velocity, you know, and if all we know is positions, we know the position, and the position, when I say position, I mean position formula, right? A position formula. How do I get from position, a position formula? Not just an x and y coordinate. That is not a position formula. That's just a point in space, right? X, y, and z, let's say. We want to be able to derive from your formula some kind of, let's say, as an example, you have a locomotion formula, something to move one object from one part of the screen to the other. How do I find those things? And that's what we're talking about here. Well, suppose that the position of a character on the screen here, like it says, is this formula. You know, this formula P at t, where is equal to t squared, right? What is the instantaneous velocity of the character times t1, right? Or t is equal to 1. So first of all, we want to plug this idea. Remember, I gave you that stuff last day. We have our little web tools that I recommend that you use. See if I can actually find them in my courses. Woohoo! Here's Desmos, right? And if I plug in x squared here, so again, I want to do one of these, x squared, you can see that x squared kind of looks like this, right? You know, you kind of have this, loop like this. Now, if t is equal to time, right? Do we care about this part? Do we care about this part? Anybody? Huh? Why wouldn't we care about this part? It'd be an alternate reality, right? There wouldn't be there's no time at negative, right? We're not going in the past. We don't have a time machine. All we care about is time now, which would be time 0, and time in the future. And you notice that this is a is a graph that rises slowly, right? Anyone know the kind of graph this is? The kind of what was that? A parabola? Yeah, kind of, but it's kind of going up like this. If there was a parabola, it would kind of loop back, right? Does this actually loop back? Let's see. If you keep going, you can see that this keeps going forever and ever, right? So kind of it's slowly increasing, but not quite a parabola. Parabola would kind of loop back on itself, right? And that's not the kind of graph it is. So in Desmos, because there's going to be some graphing functions I'm going to give you, right? If I try and give some kind of thing where I say, well, where x is greater than 0, is that possible? Well, no. But what you could do is, if you notice, and if I kind of add an item, you can see that there are different things: expressions, notes, tables, a folder, an image. You can add those things in here as well. I can edit the list. You can see that I can edit the list here. I can convert to a table. I can duplicate. That's what I'm saying. It's a neat little thing. There's some shortcuts here. As you can see that there is some stuff in here that we want to put in, right? So can anyone intuit, if I wanted to give a limit, I don't care about this part. How do you think? Can anyone figure out, and I'll leave this to you for a second, go up on Desmos for those people who have machines here. Unfortunately, this room is not made for machines, not really. But if someone's got a machine, how can I limit myself so I can say something like where x is greater than 0? That's what I really want to say here. X is greater than 0. Do I have to put another graph in there like this? So another expression where x is greater than 0, right? That's this part. You can see that it highlights in blue this part here. So tell me.
Absolute value, the little like bars on the side there should, I believe.
Well, let's take a look. We're using this tool here, right? So it's not what we're looking at. Can anyone figure it out? Let me know in a second. I'll come back to this. But all we really care about is this, right? You can see that as x approaches 0 from the left, right? You have different values. And if you hover over different spaces here, you can see that I can actually track each of the values here on the graph. This is very useful when you want to try and calculate what the value of a point on the graph is. That's why I recommend you use this tool. It's kind of a neat little tool. Okay, so let's see if you guys can figure that out. Let me go back to this. So this is the function. If I plug in a value for any value t, right, it's going to graph out that function, right? And this is really, if you think about it, similar to a position formula. If I had a position where on the screen it would start at 0 somewhere, and say top left in this case, because that's where it's going to start off in screen space on the top left corner, and it's going to go down because remember y for most applications is downward, positive downward, right? It's going to start sliding to the right, kind of falling downward, right? Which is kind of interesting. So it's going to be flipped. Yeah, there might be a few spaces over here, guys. Sorry, I know it's a packed classroom, and over there, right? Sorry about that. So we want to kind of get closer to finding what the value of t is, right? But what if I wanted to find the velocity at a certain point in time? If I have a formula for position, p at t, right, as an example, this way you say, or p of t, then I should be able to find not just the position, but I can derive the acceleration and the velocity from that. It's up? Very good. But we'll talk about that in a second. So on this page here, we want to talk about limits. And limits is the idea that if I move some x close to some other value, x naught or x0, then what will happen to the function f of x? What's going to happen if I move closer to that limit? And in the books, if you want to read the books, you see a bunch of secant lines or lines that are on a tangent to the graph, keep moving over and over again, these lines. And if I wanted to map it out, right, on the graph, for example, I want to have a line that's a secant line, with this graph here, right? And let's just put some other values in here. If I put another expression, and if I say, well, the value is 2x, let's see what happens. You can see that it does cross the line. The secant line crosses the graph, right, at two different positions, right? One at the origin, and one here at 2, 4, right? You see that? So that's the secant line. And if you keep on doing this and keep on making secant lines that approach a certain value, you can see that we're getting the average rate of change of position or instantaneous position at a particular moment in time. That's really the idea behind what we're doing. But let's talk more specifics here. So limits, right? When you look at it, here's the definition for limit. We say that the limit of x, f of x, so the function f of x, that's what it is, right? And then if you haven't taken functions, guys, think about this as a function in C# or in, if you're a Java person, Java or C++ or whatever, the function f, and we're passing an argument x into that function as x approaches a, right? At some a, or whatever a is, right? Equals to some output L. That's all we know. We don't know exactly what it is, but we can see that as x approaches a, it's going to get closer and closer to a, but never actually meeting a. And this is the notion of a limit. So something that approaches a number, on a particular curve, we approach very, very close. We can skin it very, very close. We can keep on making secant lines that kind of approach that number, but never actually get to that number, right? So why do we do that? Because sometimes we can't know the actual number, or the number doesn't exactly work because it would actually fail out. It would give us some weird number, 0, we divide by 0 or something like that. But we can give an estimate as we approach closer from the left and from the right, as an example, whether it's positive or negative. We can estimate what that value would be if it existed, right? Arbitrary close. It should say close, not close. Forget. Again, it doesn't matter which side of the value that we're looking at. Let's say, for example, a, the value a, at some a on the graph that it approaches, whether we're approaching from the right or from the left. So left means from the negative side or from the lower valued side, because if it was on a positive side of the graph, it wouldn't matter. Or from the right. As we approach that number, we get closer and closer to the value of y, as an example. Okay? Let's go back to that graph to give you the example. So here's the example. Anyone figure out how to limit it to the right side yet? Curly brackets. What, right afterwards? Like this, right? And then x, where x is greater than 0, right? You can see that that works, right? Thank you. It's a very useful, like I said, very useful site. I highly recommend you get used to it. So you can all we care about is values of t that are positive because t is equal to time. Okay? So therefore, just keep this in mind now. If I was to do the same thing for values of 2x, and you'll see why I'm getting 2x in a second, so where x is greater than 0 again, you can see that we have a line that looks just like this, right? And it's going to go off into infinity. Okay? And furthermore, if I have another function, so I'm going to put another expression here, right, where the value is just 2. Can I do that? Can I just put like a value like 2 like that and then, you know, sneak away? Well, the problem with putting a value in, what was that? If I put equals to, let's try equals to like you said. So if I say equals to 2, that won't work. How about x is equal to 2? Let's try that. Because we need some kind of formula, right? There's x equal to 2, right? Where x is equal to 2, right? And by the way, this is a great thing is you can also change the values, so I can kind of scale across to test different values where they kind of intersect, right? That's right here. So that's kind of neat. I want to go to 2 though. So x is equal to, it's almost like a scale that I'm using. And you can pull, I think you can pull these down so you can order them the way you want. These two values are all relative. They're all related to each other in some way or another. But notice how as each value approaches x is equal to 2, right? The limit, right? Let's suppose we're trying to find the value of y as x approaches 2, right? What is that value? So if we start off down here, you can see as it approaches 2, we get different values. Here we are. We're sitting at, you know, y is equal to 2. And as we keep going, you can see that y is going to be about 4, right? Makes sense? As we get smaller and smaller values approaching 2 but never reaching it, it almost becomes 4. If you guys can see that, right? So it's interesting the way how when I use 2x, and this is why we're talking derivatives today, that we can find the instantaneous velocity at that time, at that point in time. All right, let's go back to this. So that's really what limits are. Limits are our ability to find the instantaneous value at a certain point in time where we can't actually get there for whatever reason, because we don't have the equation, because maybe it's illegal if we put the value of whatever it is there, we get something that doesn't make any sense mathematically, something dividing by 0. We can approach that value so we can estimate it. That's what limits are. So when are they illegal? Dividing by 0, square root of a negative number, a logarithm of 0 or negative, right? Logarithmic functions. And so we have this theorem, right? We can use direct substitution to substitute in to find the value of a. So let's say in this particular case, we're using this limit of f of x is equal to the function f of a, right? As we substitute a number in a, let's say, for example, I have as x approaches 2, then we're actually passing 2 into the function. That's all we're doing, okay? And it's an estimate of how, as we approach that number, but never actually get there. Okay, this is why we do limits. There's a bunch of stuff. Again, I'm going to share this with you. Let's just zoom in here to the ones you really need or care about. So here we're just going to go up here. And you can see that, suppose that c is a constant, and that the limits of x approaches a, f of x, and the limit of x approaches g at x exist. Both of them exist. We have to see that sometimes the limit won't exist because it violates one of those other rules I talked about in the previous slide. Divided by 0, square root of a negative number, those kind of things, right? So assuming that both of these limits exist, the limit of as x approaches a of f of x, and the limit of x approaches a of g at x, f of g at x, if you will, then we have these limit laws or identities, if you will, right? Where, for example, the limit of as x approaches a of f at x plus g at x, right? If you take these two functions, it's like saying, I want to split these up, and I can actually split a limit of x approaches a of f of x plus the limit of x approaches a of g of x, and we can split them off into two separate functions. Now you might say, why am I showing you this? Because remember, we want to find limits sometimes, and they're so complex, we need to split them up and do a few manipulations in order for us to see that the limit exists or not. And there's a bunch of other ones that we can go into, and I will do this during lab, but I wanted to show you that there's several identities here. One of the interesting ones is where I have a limit of a constant is a constant. So if I have a limit of 1, it's 1, right? And a good example of that is if I go back to my graph, right, and you can see that the limit of 2, because x is equal to 2, is 2, right? It's a limit, right? There is no other thing to put in there. Limit of a constant is always the constant that I'm looking for, okay? But what if I wanted to find the limit as x approaches 0 of 2x, right? Now, can I? Well, I said x is greater than 0. But let's say if I say greater than or equals to 0, I can also do that because x can also be, t can also be 0, right? We're just using x for t, right? And again, I can go down in here and say greater than or equal to. You can see that it also crosses 0 here, right? And the same thing goes for here. I want this to be greater than or equal to 0, right? So these are the two options. Okay, here we go. So you can see that it can also be 0, right? Because t is also 0 times 0 when you first start off, right? So if I say that the limit of as x approaches 0, right, where of 2x, what is that? And if I multiply, if I use the substitution law, right, that we talked about, and I substitute 0 in there, then the value is 0, right? As x approaches 0, let's take a look at this. As x approaches 0, then the actual value that we're getting is 0, right? And I can do that for any point on the graph, on the the graph, which is this line here, the green line. Okay, notice that these are the colors on the left-hand side, and it corresponds to one of the graphs that we've drawn. Okay, guys and girls, nothing spectacular, fantastic here. We're just reviewing. Who's never done limits and derivatives before? If you've never done it, then this is something new, but this part is fairly straightforward. There's no creativity in this part, okay? Really, it's just you substitute, and if it's possible, you'll find out that it's possible. There's a couple of tests we have to use to figure out that the limit is possible, or if it's not possible, and we'll go over that in a second. Let's go for some other ones. You have a constant multiplied by a function. Well, what you can do is you can take that constant out, and you can remove it in front of the limit. So for example, if I had a constant 2, and if I was getting it's like saying, I want to get 2 times the limit as x approaches some value of x, right? It's exactly the same thing. We just saw that inside of our 2x function here, right? Because I can separate it out. I can say, well, if I wanted the function of x, right, not 2x, so let's just replace this with x. Here's x. You can see that this is a straight line here, right? Just like the other line. And if we multiply that by 2, what we're doing is we're actually scaling it, right? We're scaling it up, but it looks almost identical, right? Almost identical to this one, right? And so we can separate both the constant. We know that the limit of a constant is just the constant itself. And if we use substitution for the regular graph, then that's fine. We multiply it by the constant, and then we get back to where it's supposed to be relative to how the graph is sloped. Okay, so that's what this law means here. Why am I sharing you these laws with you? Because sometimes you're going to get a question that is, you have to do a little bit of massaging. I think I like to say that, right? Before you get the answer. And this is where students in general have trouble, because they're like, I don't know what massaging to do in order for me to get there. It's really troubling. I don't know which approach to take. And we're going to talk about those things. All right. Here's one that's interesting. So this one is interesting in terms of we can separate a plus or a minus. So positive, if we add or subtract, we can just separate them into 2 different limits. That's one option. Here's where we have multiplication. So I have the limit of f of x times g of x, right? As an example, we can actually separate those 2 out as well and multiply the results. So there's the commutative law. And now this is interesting in that the limit of f of x over g of x is equal to the limit of, as x approaches as a, of f of x over the limit of x approaches a of g at x, provided, like it says here, because remember, limits have to work, that g at x cannot equal to 0, because if it was equal to 0, somehow of some value of a was equal to 0, it would make this limit undefined, right? Because it would be something over 0. Right? And this is interesting as well, where you have the limit as x approaches a of f of x to the n, right? The whole thing to the n is equal to the whole thing to the n, which is interesting, where n is a positive integer, can't be a negative integer, because then you're going to get that same negative logarithm. Okay, so a few identities here. And here's another one. The limit of x, which is what we just did, is equal to a where x approaches a, right? So if I have just value x, there is nothing else I'm multiplying, then it's going to be equal to whatever the limit's approaching. Okay? So very straightforward stuff. And there's some other ones that we'll talk about, right? For x to the n is equal to a to the n. That's interesting, an interesting identity, right? And this one's interesting as well, where we have x to the 1 over n is equal to a to the 1 over n. And so why am I showing you these things? Because you can do a simple manipulation sometimes to find the answer. How far do I want you to go? Sometimes that's the question. And the answer is, it depends, but I don't want you to simplify all the way down. We just don't have time for that on a test. And we'll talk about when to stop in lab. Okay? Any questions so far about limits and substitution? That's the first law. The first law of limits is substitution. I feel like, a philosopher. All right. Okay, let's try this out. So if I was going to find this crazy limit, and this is the kind of limit you're going to get on a test, right? How do I figure this out? What is the answer? Have your papers, please, and I want to find this out. Right? Yes?
And you think that sets the denominator to 0?
Well, let's take a look. So if we figure out, if we replace, remember, we're doing substitution, and we're taking -2. So as the limit approaches -2, right? And we're substituting -2 in there, right? So negative of -2 to the 2, right? It doesn't look to me that there's anything that's going to be in here that's going to make the limit not existing. Why? Because unless cos of 2 pi, right, is greater than something that we're getting over here, chances are the limit exists. Do you see that relation? Right? Yes?
So in this, x is -2.
X is -2. That's the limit of as x approaches -2. Correct. We're using substitution. We just substitute x in there, right? And if that's true, if you actually substitute everything in there and go through it, does the limit exist? Anyone tell me if the limit exists?
Yeah.
The answer is yes, right? Why? And this is me without figuring it out. We're going to figure it out in class, in lab together, right? I'll actually do the math with you on the board, right? But take a look at this. You can easily just look at this bottom part. And the biggest concern for me is this part, right? And also, here's the other part. The minus 7x is 2 to the x, so 2 to the negative 2, right? 2 to the negative 2. What happens when we do 2 to the negative 2? What is that? It's 1 over 2, right? So it's actually, that's kind of a weird thing to put 2 to the negative 2. But it can be there. Is it going to be greater than or somehow equal to make minus 7x 0? No, chances are. So we're safe here. Nothing that I can look at any of these terms. Now here's something that I could probably think about. Could I break this thing up? Yes. No, you know, based on the limit laws above, I could split this whole thing up into different parts. But we probably don't need to. Okay, so this is an example. I want you to try and work this out. Again, we'll work it out in lab. But the first thing to note is, can we easily tell that the limit does not exist? Here's another one. How about this one? Does the limit exist? The way it's written, right? The limit does not exist. Why is that? Because as x approaches 3, right, it's going to be 3 minus 3 on the bottom, which is going to be 0, and then we're going to have a problem. But is there a way to solve this problem? What would we do instead of doing this? Remember, we talked about massaging first. What do we got in the back there? Wait. I got to I'm going to come back to you in a second. Tell me. Factor, right? Oh my God, we're actually talking about factorials again, right? Yeah, you have polynomial equation up top, right? Ax squared plus bx plus c, right? We don't have the bx term. That term is out. We have c minus 9, right? We have ax squared, where a is equal to 1, right? So how do we factor it out, right? How do we factor this out? Something, whenever we factor, just to remind you, right? It's something that equals to, when we factor two things together, it's something that equals to x squared. So remember, we do this x times x is equal to x squared. That makes sense, right? And then something that's equal to minus 3 on one side, right? But no x term, no bx term, that part. So that means it's going to be x plus 3 in brackets times x minus 3, which the positive and the minus are going to cancel each other out. So you're going to have on top x plus 3 times x minus 3. And if x minus 3 over x minus 3 sub out, which is going to be 1, right? And then you're left with x plus 3. We'll do this in lab, where now you can figure it out, right? Because x plus 3, if you take the limit as x approaches 3 of x plus 3, you're going to get 6. And that's the answer. You guys see that? If you don't see that, wait till lab, and I'll show you that example on the board, okay? But that's how it is. So sometimes we need to massage the limit that I've given you in order for you to get the answer so that it's doable, okay? But immediately when you look at this, you're like, hold on. We can't have anything over 0, which means this limit's not possible. It doesn't make any sense, but actually it is. All right. So everything right now we've done applies to approaching a limit from only one side. But for us to confirm that a limit exists, we need to approach it from both sides. And we have some funky syntax. Here's an example. If we say the limit of f of x as x approaches a from the left equals L, then we write x, and you guys can't see this. I wonder if I can make this a little bigger so you guys can see the actual thing. There's like a little minus on the top there. That's the notation. So x approaches a minus. That means x is approaching a from the left. That's just the notation to tell us the syntax, if you will, in this mathematical language of ours, to tell us it's coming from the left. We're approaching it from the left. And both of those limits must exist if we want to prove that the limit exists, right? Otherwise, the limit does not exist, or it is not possible. DNE is what we say, does not exist, right? So here's something. The limit of f of x is equal to 5, right? Where x is less than 1, right? We want to find this one. And what do we do when we find the limit of a constant? It's the constants, right? So that exists. See how that works, right? How about the limit of f of x as x is greater than or equal to 1, right? That's, from the right. And if you substitute 1 in there, the root of 1 plus 1, that also exists, right? But the problem is there's a bit of a displacement here. Can we map this out? Let's try this out. So if I take these values, right? Let's try this out. So I'll say x here is equal to 5. That's what one of the ones we had in there, right? Here's x is equal to 5. And we only care about the root x plus 1, so let's get rid of one of these. and we'll say root x plus 1. We'll put all those brackets in there as well. And if I want to find that here, you can see I want to find the root, right, of, I can do this properly, plus 1, right? You can see that it expands. And just make sure that x is greater than 1, not greater than 0. There we go. Root of x plus 1 is greater than 0, right? That's actually inside here. X plus 1 is greater than 0. And that'll be okay. How about that? There we go. No, this one's inside. See, it's under the square root. I'll be okay. Thank you. Root of x plus 1. I'll be okay, like this. Right? As x approaches 0. X approaches 1. And then x is equal to 5. We want to put in there where x is less than 1, if I'm not wrong. Right? X is less than 1. And you can see we have, there won't be, when we won't show x is 5, where x is less than 1. But this one, we can see the graph is kind of weird. It kind of goes really, really flat for a long, long time. Right? Does that make sense? Anybody have anything else to say on this one? What was that? Y is equal to x, square root of x plus 1. That's what it is. Okay, let's try it. Maybe it's a misprint. And then if that's true, look. There we go. You're probably right. And then so notice that there's, yes, thank you for that. So notice that there is a separation between the two. They're not connected, right? They're not connected, right? And this is the problem we do when we look at a particular formula, right? Because you can have a formula that in the game too, right? You can say, well, if the value is in pixels is this on this side and this, does it exist? And you can see that we might have a problem. Okay, because it doesn't, those two don't connect. If they don't connect, we can never get to that limit here, right? So the limit does not exist. So, so here's the theorem. So as the limit of f of x, it's equal to L, whatever that limit is, if and only if, so IFF, that's a short way of writing it in math, if and only if the limit of f of x approaches, as approaches a from the left exists, and the limit of f of x as x approaches a from the right also exists. That's the only way that this can exist, right? That's the test we can make, right? That's a great little test, right? Because we can plug in other numbers. We don't have to plug in the final number from substitution. That's just one way of doing it. This is another way, right? So think about smaller values at approaching, but never getting to that particular value to test whether the limit exists from both sides. Okay? I'm just trying to give you some tests to understand how limits work. All right, how about this limit? Does it exist? All right. And again, I want you to figure this out you should be able to look at it first. First of all, this is weird, right? Because we have this to the 4, right? That means it's x minus 2 times x minus 2 times x minus 2 times x minus 2, all in brackets. That's what it means, right? If I say it's equal to 2, no matter what I do here, it's going to be something over 0, right? And if I plug this in, you can actually plug this function into the graph, right? Okay, let's try this out. Let's try and plug it into the graph if we can. -5, so I'm going to get rid of this one, right? And let's see if I can do it. So it is, and I'm thinking I can probably do something like this. Do I have something over something else? Like at this part. I'm probably guessing it's -5 slash. Yes. -5x, I'm just checking, right? -5x over x minus 2 to the power of 4, right? And this is the graph, right? And this is why it's so interesting to look at graphs to see the limits. Does this limit exist? It's asymptotic, right? You can see that they never, ever meet, which means the limit cannot exist, right? DNE, this limit does not exist. Why? Because this function here, when we look at this function, it doesn't work both from the right and from the left. We don't have a limit that works both sides. So because we don't have a limit that works both sides, we can say that safely the limit does not exist. Does that make sense? You can see it graphically here for you, right? Is there something to massage this to make it work? Not that I can see, right? You can't do anything to the bottom or whatever to make it so that it's more understandable, is what I'm saying. Questions so far? This is the heart of limits, really, at the end of the day. It's understanding about, using substitution to figure out the value. That's it for limits. I got some questions that I'll go over with you at the lab.
We're not doing like secondary
Those ones, right? All right, now if I start doing secondary limits, okay, so let's go back to that. You're talking about limits, secondary limits, limit of, the limit of, right?
Yeah.
Yeah, we're not going to do that. Yeah.
Wasn't there like getting a common denominator or something like that, or expanding parentheses? Two other ways of getting one method, like if you run into the zero.
There's other ways, and what you do is what we talked about. We use algebra, some ways of separating things out, right? Could we have used any of the methods that we talked about earlier to use algebra or some limit theorem to separate things out? And we're going to do some together, but really there's nothing that I can see. All right, so what is a derivative? So we've got limits, the idea of limits, right? We've got a line, and we want to find the instantaneous value at a particular point on the actual line itself, this curve, right? And what we want to talk about when we talk about derivatives is this idea of rates of change. Rates of change. So it's the instantaneous rate of change of a particular function, whatever that function is, right? That's what the limit is. Also, if you think about it, it's the slope of the line tangent to the curve, right? So whatever that tangent line is to the curve, the slope, that's all at that particular point, that is the derivative. All right, that equates to the derivative function. All right, so here's example, a single line, single point of intersection on this particular tangent. Notice that there are many, many tangents, depending on which point you're talking about, right? So again, we have limits. We can think of our original problem, how to find instantaneous rate of change for a function at some point A. We don't know what that is yet, right? But suppose we want to find the estimate, the instantaneous rate of change of A, where we have A and then some A plus H, right? And so think about the graph, the curve, right, that we're looking at, some kind of curve. And even if it is a line graph, right? So let's change this to, again, 2x. Make this curve, right? And if if we actually label this, and if where A is equal to this line here, if I look at where A, I'll bring this in closer for you guys to see it. Really close. Here's 2, and here's 3, maybe too close. So let's suppose I want to find a value where y is 2, right? As an example, here's y is 2. You can see that x is 1, where y is 2, right? Does that make sense? Because it would be, right? Because if you sub in 1 in there, then y is equal to 2x. That's what it is. And if I put that in there, I don't know if I can do this, but I think I can. I can make an equation like this. Y is equal to 2x. And you can see where y is equal to 2, then x would be equal to 1, right? Very simple. But what about this, where we have a line up here? So we have some A down here, right? And we also have some A plus height, another height, right? And we're going to get, smaller and smaller. We're going to get almost like a limit again as the height decreases and approaches the limit of 2x, right? As where x approaches 2, you can see that it's going to get closer, y approaches 2, then the limit of x is going to be 1, right? How do we figure this out? What happens, and how does this work? Well, that's how it would be when we want to find the average slope of the line between A and A plus H, where some value H, some value height, where H is height. Okay, let's go back to the graph. This is the height of the graph. This thing here, right? Remember we talked about triangles. This is the height of the triangle that we're talking about here, right? And just to make it seem that it's more plausible, we'll just add in an expression where, I don't know, we'll put in where x, as an example, is equal to 2, just to make that look like a triangle. X is equal to 2. There we go. And there's a triangle for you, right? So imagine that the height is this value right here, right, along this line. Okay. So it's some a plus h. That would be a plus h. And here's a, where the value of a is 2, right? You can see as we approach 2, right? And we get smaller and smaller values. Let's do smaller and smaller values. As we approach 2, like this, right? Then x must be 1. Okay, as you can see that. And it's very similar. So derivatives, they've come from limits. The idea of limits created our notion of derivatives. Okay, that's where they came from. And here's an example of that, where we have a limit as h approaches 0, right? Can we do this thing? Is this doable? It's not, right? Because if h was 0, then we would have something over 0, so then it would be unapproachable. There'd be nothing that we can get for instantaneous, the rate of change for this particular function, because it's something over h, right? So we'd have a problem with this one. So therefore, what we want to say is, where m is the slope of the line that's tangent, to that particular function, whatever it is, right? And it gives us the instantaneous rate of change, or whenever we say instantaneous rate of change, substitute that whole line of wording for derivative. And that's what the instantaneous rate of change is. Rates of change means a value that changes from one value to another, an average change of values from one value to the other, given a slope or a line. The function that gives the rate of change at every point is called the derivative function. And that's really the definition of a derivative. So knowing that definition, then, here are some derivative rules. So the derivative of constant is 0. Why would that be? Because the constant doesn't change. There's no rate of change. Therefore, it must be 0. There is no. If I'm trying to find the instantaneous rate of change for a constant, but there's no instantaneous rate of change for a constant. So that's why it must be 0, right? It makes sense if you think about that. If you just have in your mind, when I say I want to find the derivative, right, I want to find the instantaneous rate of change. How about if you have something to the power? We use the power rule for that. So if I have d over dx, right, which is the derivative, right, d over dx, right? That's how you write derivative of x to the n, right? Then what we're going to get is this value, and I'm going to bring it closer so you can see it, where whatever n was, let's say x squared, if x was to the 2, you take 2 minus 1, so it'll be 1, x to the 1, which is just x, and then you pass down that n to put it in front of it as a constant, so it'll be 2x. That is the law, power rule, right? So what I was writing before then, when I was writing these equations, and I said something like x to the 2, right, x squared, is equal to 2x. So we say that 2x is actually the first derivative. And Corey, yes, we will have multiple derivatives, first and second and third derivatives of certain things, because we need to do that to get acceleration from position, right? Position is our initial function. Our first derivative is velocity. Our second derivative is acceleration. It means we take the derivative of the derivative. So the second derivative of 2x, right, is 2, right? And that would be our third function, right? That's our function where x, right, as an example, like we said before, is equal to 2. So I actually gave it to you right at the beginning, and that is the acceleration. So in this particular curve, right, if you want to find the instantaneous acceleration of any object on this particular curve, right, it must be 2 at any point, x. Does that make sense?
But that's as far as we're going in this course, right?
You mean you don't want me to do more?
Okay. I don't want to, but somebody else might.
I'm not going to go with more than second derivatives, right? Because there's no need for it for us. For us as programmers, we're not mathematicians. Chances are we won't need to go beyond the second derivative, okay? Remember, this is math for games kind of thing, right? And same thing with physics for games. We're not going to, just like I'm not a mathematician or physicist, neither are you. Chances are. I don't know if anyone, is anyone a mathematician or physicist here? So if you are, like, maybe you can come up here, But I'm definitely not, and I know this would be enough for me, these three things here. So this would be the first derivative, this is the second derivative. So that means that for any x, for any value x on the curve, the velocity then is 2x. how does this work? So if x squared is our function for position, right? That means y is equal to, really what we're saying when we say our position function, we're saying for some value of y, you know, is equal to x squared, right? And for some value y is 2x, right? And we can't say for some value y is x is equal to 2 because it's a constant, right? But one thing we can know is that for every value y, x, you multiply x by itself to get the next position, all right? Where y, if you look at y and x's positions on a screen, right, you can find the next position. So if I was going to make an alien with this boring curve, x squared, some weird curve that went like this or down, right? How could I make this curve differently? What if I wanted to make another curve that came from the top down? What would be my equation then? What was that? X to the negative 2. Okay, let's try that out. So if I go x to the negative 2, then it gives me this. Was that what you meant? Okay, let's see if it's negative x. This is where, like I said to you, it's really neat. That's what we want, right? And of course, I wouldn't want just negative x. I'd probably want to build this up a little higher. So if I said plus 10, right, then I could probably make it something like, so 10 is the translation, right? And this would be the curve that I'm talking about. So I can have a curve of an alien that kind of drops down this way, and maybe another curve of another alien that goes the other side, right? What if I want to make it squirrely? I want to make it so that it's kind of like a sine wave, but on the y-axis as opposed to the x-axis. What could I do? So I can't, I mean, can I use sine? I could. I mean, I could use sine of x. So let's say if I go plus, if I can type sine of x, right? That kind of gives me a weird graph, right? But you don't see a lot of changes here. It just shifts it over a little bit, right? And the only way to see this would be if I multiplied everything here. This is where this can get really nice, right? By, let's say, something like 4, right? And then I translated everything by, let's say, a value of 5, right? So you can see that that's a different kind of curve. See how it's coming like this? And so the alien comes up and then comes down, right? So it comes up and down as a pattern for, like, I'm talking about a top-down shooter game, let's say, right? So I want to find the instantaneous velocity of this. What's the derivative of this function? How do I figure this out? Well, you break it up. And I'm going to show you this down here. So the power rule is the first thing we learn, right? Constant multiplying rule is the second one, right? So the constant multiple rule, we take the constant out. So if it's derivative of c times f of x, right? We just take the c in front of the derivative, and we just find the derivative of f of x, and then we multiply it by c. Same thing that we did almost for limits, and this is where they came from. You can notice that the limits and the derivatives have some rules that are almost identical, right? Because they are kind of, forgive me, derived from each other. Here's sum and difference rule. It's exactly the same as the limits, right? Sum and difference rule for limit almost looks exactly like the sum and difference rule for derivatives, right? Well, if that's the case, if I'm going back to my function over here, I've got some weird function, right? Now, what's the same as this? I would probably do something like the following. I've got some kind of constant that I'm adding, right? But I've got this function 4, right? Multiplying it. Now, if I didn't have this, it would make it easy, right? Let's just do this. Let's say this is the function, right? If I didn't have that, I can just take 4 and get rid of it, and then multiply everything by 4 after, right? That's what we're talking about here. And if you look at the derivative, then it would be the derivative would be, if you just, let's put the derivative down here. Who can help me out? Come on. This is pretty simple. We don't know what this derivative of sine of x is, but we can probably figure that out, right? So if we don't worry about the things, we say minus 2x, right? That's the first part, right? Plus, what's the derivative of sine of x? See if you're right. I'm going to put down what you're telling me, but we'll go back and check the derivatives. David, look at the graph. Look at the graph that we got now, right? And now we want to multiply everything by 4. So we get whatever that derivative was, and we multiply it by the value that we had before. We don't kill that thing. Here it is. And if you notice, that would be the derivative. That's some weird value. Let's just get rid of this one. Oh, actually, let's not get rid of this one. That's the value. But you can see that this is the velocity function, relative to this position function. Okay. Now, it might not look like it's really intuitive at this point, but we've got some really weird function here that I made, right? So it's not like exactly. So if you notice, as x approaches 0, then y becomes negative. Right? That's what happens here. So in other words, it starts slowing down, right? That's what this function tells us. It tells us as x approaches 0, if we're going to use the limits, that y becomes more and more negative, right? Which means it starts slowing down. Y slows down. The velocity is actually slowing down, right? Let's take the second derivative of this thing, right? By the way, first of all, do we actually keep this 4, or do we get rid of it? Right? Well, let's continue. And I'm going to move this down here so you can see it. So this is the blue line. So now we're going to take the second derivative, right? And again, we'll leave the y in there so you guys can see that it's just another function, right? I want to take the second derivative now, right? And again, if we just don't think about the derivative, we know that the derivative of negative 2x is what? Negative 2. That's the first thing. Take a look at that line, right? And then the derivative of cosine of x is minus sine of x. We'll talk about that in a second. So say minus sine of x. Let's take a look at this thing. I'm going to give it to you in a second. It's actually on the PowerPoint, right? And I'm also going to put it on your tests for you, right? And then multiply the whole thing by 4, right? Because that is the rule that we saw, right? So we take the whole thing, right? Multiply it by 4, if we're not wrong. And you've got this thing. And now you can see what happens here. So for every point x on the y-axis, you can see that it goes up and down. Why is that happening? Because in this particular case, our acceleration changes because of our wild graph, right? It accelerates and decelerates, accelerates and decelerates. It goes faster and slower. That's the kind of motion we're describing here with math. So, yes?
The first derivative, aren't you supposed to bring 4 over to the other side and divide it by the...
Let's take a look. So here's this. And you see, am I dividing?
Yeah, because that's
so
you're multiplying the entire.
So this whole thing is multiplied by f of x, right? And all I'm doing is bringing it out and multiplying it by f of x. That's all I'm doing, right? So I take the derivative of f of x and then I multiply it by the constant that I had in the brackets. That's what I've done here, right? Every single time. So again, some difference rule we figured out. That's not much of a difference here. Let's go to the next one. I'm bringing them really high so you can see these ones. Here's one, the derivative of a logarithmic function. So here's the f of x at a to the x, right? What's the derivative? Log of a to the x. And again, that's why I'm not going to tell you that you need to remember these things. Did I miss it? I think I missed a slide. I think I did. I missed a slide for sure. We're missing a slide. Oh, here it is. It's out of order, right? So Euler's number E, right? It's the real number, right? So we always know that here's the rule for Euler's number. E of x is equal to E of x. Derivative of E of x is equal to E of x. All right. So whenever you see Euler's number E inside of some kind of question I've given you, just it is E of x, whatever it was before, right? Why? Because, and here's why it is that way. E is a real number, right? As h approaches 0, right? And if you do that, you figure out that this e to the x is equal to the same value. All right. Here's the difficult one. I'm not going to tell you that it's the easy one. This is the more difficult one, okay? You need to know, well, again, I'm going to put these formulas on there for you, but sometimes what you have is two functions, f of x times g at x. And you want to find the derivative, right, of both of the functions. Now, this is not like saying x squared, right, plus x. It's not like that. Or x squared times 2x. It's not like that at all. It's like two different values. So another kind of function altogether. I have two functions, and I'm multiplying them together. How do I find the derivative? Well, it's called the product rule. And you may get questions like this, right? Where you have the derivative of, so I'm going to simplify this for you as much as I can. So f, notice we also put this prime up here. That's another way of writing the derivative of. There's two ways, d over dx. And this little symbol looks like a minute symbol. That's prime. You say the prime of, or the first derivative. Double derivative has two of those marks, right? Okay. So for the derivative of f times g, where f and g are both functions, then you take the first function, f, multiplied by the derivative of the second function, and then you add the derivative of the first function multiplied by the second function. Okay, now this is, you might think that, why, right? Why would you do that? And what ends up happening is, especially when you have one function inside of another one, right? Like f at g at x, that kind of thing, that can happen as well, right? So derivatives are kind of straightforward. There's rules. If you follow the rules, you're going to get the right answer, okay? That's the bottom line. There is no creativity so much with derivatives as there is with limits. Limits, you may have to do some fooling around. Derivatives, you need to do some fooling around, but only with the derivative laws. Whereas limits, you may have to do some manipulation. Sometimes you get that as well. Let's find the derivative of this, of h at x, as doesn't matter what the value. This is the function h at x, where it's equal to 3x plus 1 and 8x to the 4 plus 5x. How do you figure this out? Let's do it on the graph again. All right. So by the way, if you don't understand, put up your hand. This is the time to do this, right? So let's type this in. So again, we have, let's get rid of all this. So 3x plus 1, right? And we want to multiply it by 8 times x to the 4, right? Okay, notice I'm going to move my cursor down again, plus, right, 5x. Okay, that's the actual curve. And that's a really weird graph. Take a look at this. It's hard to see, but the graph, if I zoom in, kind of looks like this. Interesting movement. So imagine this is your position function. You write a position function, so an alien has a certain pattern that it follows, or it could be some kind of other obstacle or danger or something like that. Or maybe this is the way the physics work in your world, where you have some kind of weird thing happen. So this is the position function, right? Help me find the acceleration function, or sorry, the velocity function. So what's the first derivative of this one? How do we find that out? We need to use product rule. Remember? This is the way I look at it. I always remember it this way. Derivative of the first times the second times, derivative of the second times the first, kind of thing. Right? I always think of it that way. So you take the derivative of 1, doesn't matter which one, by the way, because it's commutative, right? So if I take the first one, I copy it, and then take the derivative of the second one. I'm just doing it this way. Doesn't matter how you do it. So what's the derivative of 8x to the 4 plus 5x? Well, we know that, right? It's 32x to the 3, right? Remember, it's x. The power rule says you subtract 1 from the power, right? Plus 5, right? Because you get rid of the x. There is no something times x is just that's that constant, right? So that's the first part, okay? And now what we want to do is we want to add, right, the derivative of the first, right, times the second. So what's the derivative of the first? Derivative of first is 3x, right, or 3. Wouldn't it be 3, right? Because 1, the derivative of a constant is 0, right? The derivative of 3 times some value x is just 3 in this particular case, multiplied by the second, which is in its entirety. I'm just going to copy and paste if I can do that. See if I'm lucky enough to do that in this little thing. Oh.
There you go.
Crazy ass, right? Sorry, so we're dealing with other foreign properties, and that's your derivative. Hey, question: Do I have to take it further? Do I have to take this further? How can I simplify this more? Should I simplify this more?
Sure.
No. Don't want you. Why would you? I mean, Sure, you could multiply 3 by this, thing. So you could get like 24x to the 4. I mean, that might be an easy multiplication or whatever. You could collect like terms, but that would just take a lot of time in the exam. And then I would know already that you can do a derivative, and that's all I care for. Okay? I don't want you to simplify past this point. It's not necessary. Truly. Yes?
What would stop them, for instance, from actually multiplying the equations and then deriving the result?
You could do that too. That's another way of doing it. So Hercules' question was, what stops me from factoring both equations, multiplying both equations, and then deriving the results? And you should get the same result at the end of the day. Nothing stops you, right? But why would you? If you know this is the answer, this is the quick way, this is the product rule, right? Then we're good to go, right? Now here's where you want to simplify, okay? Now I want to find the second derivative. Now it's a little hairy. I've got two pieces. I want to find the second derivative, another derivative of this derivative, right? How do I find the second derivative of this derivative? Now, you know what? Maybe you need to simplify a little bit now, right? Because if I expand this or whatever, so I take the 3 multiplied by the 8, let's get 24. Let's just expand this like this. Just bear with me while I do this, right? So I multiply this as 24, right? And this is plus 15x. Let's just make this, it's the same graph, right? I'm just expanding. Do I want to expand this one? Probably not. That means I have two terms, right? I have one that I have nothing to do. There's no multiplication to do here, right? But here, I got to use the product rule again, right? And now I'm going to do the same. I'm going to get the next derivative, right? So here's the third or the second derivative. So what's the derivative? Let's do the derivative or the first times the derivative of the second. So I'm going to take the first value, so 3x plus 1, right? Times the derivative of the second. What's the derivative of the second, please? 96x to the 2, right? Right? Do I have the plus 5? No, because it's a constant, right? Oops. I know he's good, eh? Plus, and what's the second part? Let me see if I can expand this. Plus this derivative, right? Oh, no, we're still doing this part, right? We're still doing this part, right? So plus the derivative of the first, right, which is 3, right, times the second, which is the second. It's in its entirety. I'll be okay. So I might as well just copy and paste. Let's see if I can do this without killing again. Right? Right, that's it. Plus, now the derivative of this piece. What's the derivative of this piece? So 4 times 24, someone? Is it 96? 96, oops, 96x to the 3, right? Plus 15. Are you confused? Good. That's the product rule. Guys, I'm teaching you like, I guess grade 12 calculus in one day, right? Like, I mean, it's, what was that?
90 hours skipping most of the steps.
But that's how we have to do it, right? So you can see that this is the first derivative. Let's say this was the, and you can see the functions here, which is kind of neat. You can see the different graphs. You can see the different graphs here. This is the green graph. But take a look at this orange graph. The orange graph is the instantaneous rate of change of acceleration. So this is the acceleration curve. This is the velocity curve. This is your position curve. I'm just doing this over and over again so you get it in your head. First derivative, second derivative, right? When we do integrals next week, we're going to go from here to here to here, which is way more creative than going this way. There's no creativity in doing derivatives. There's lots of creativity going back. How the heck do we find the antiderivative, which is what we're going to be talking about next week, right? That's why I'm stopping. I'm not going to talk too much about derivatives. Let's take a short break, guys. Do 5 minutes for washroom, and I'm going to have a little bit of this coffee that was bought for me. I want it out of respect, and we're going to keep going with derivatives.